Today you're going to learn about energy. Just kidding. So today we're going to talk about energy. We're not going to do the chapter 14 notes. Take a look in your purple packet. We are going to stop at page whatever the heck it is. What page should I actually be flipping to? 189. So we're gonna do everything from 189 to halfway down 192. Eventually we'll do the other half. The other half is solids and liquids. We're just going to focus on energy and how it moves around today. The math in this chapter is minor. It is multiplication and subtraction. We're not really going to do much with moles by any means. So we're going to study energy for a while. This is such a popular topic, it has its own name. It's called thermodynamics. Thermodynamics. Therm is a prefix or Greek word that means energy. Means energy or temperature. And we're going to kind of talk about how it can move. What is energy? Energy is kind of a hard thing to visualize because you can't hold energy in your hand, literally. You can hold things that have energy, but not actual energy. There's not like energon cubes I can hand you as if you were a transformer. But energy is a thing. It moves from different substances. How many of you just ate lunch? Right, good job. Almost everyone put their hands up. Sorry to see that. You didn't eat lunch. Oh, okay, good. Anyone else have the Tatinos or whatever they're called? What are they called? Tachos. They were great. I enjoyed them today. I can't believe I just recorded that. So energy is the ability to do work or produce heat. We're going to have to talk about work is, what heat is. People have a concept of what heat is. Heat is energy flowing from one thing to another thing. When something feels hot, like watch, I'm going to hold this guy's hand. Hi, how you doing? It's good to see you again. His hand to me feels warm. My hand to you feels cold. Very good. Good. You have observational skills of a kid. So energy is flowing into my hand and out of his hand. If his hand feels warm, it's leaving his hand and coming into mine. Do you understand that idea? That there is something leaving him, and by the way, I'm still holding his hand. It hasn't gotten awkward yet. It's leaving his hand. That is heat. The energy flowing, we call that heat. The other type of energy is work. And work is done when you apply a force across a distance and you move something, you're exerting a force. We don't do that type of work very often. This sort of energy is more for the physics. Oh no, you're going to hit the wall. That's more for the, I wonder what that's going to sound like at home. You know? Potential energy and kinetic energy. The most common example is something like this. Like there is a building. Here, look, these are windows. Yeah. And there are 3 kids. Kid A has a ball. Kid B has a ball. Kid C has a ball. They all hold the ball out of the window and drop it. Right before they drop it, which ball has the most potential energy? C, because it's got the farthest to fall, right? Boo, boom, 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 versus boo, boom, 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 and boom, boom, boom. Evidently the ground's not even there. Which one has the most kinetic energy? Trick question. Before they drop it, they're all the same because they're not falling yet, right? But when they get right before the ground, like that moment before they hit the ground, C would have the most kinetic energy. It's moving the most. We don't do energy like that. Did anyone have straight sugar for lunch? Yes, shocker. Yeah. A guy? Yeah. 14 people just raised their hand. No, straight sugar. You go on this rocket high afterwards as the sugar crashes into your system, and then this crash afterwards. Because real quickly, the sugar helps your body make energy and converts adenine diphosphate into adenine triphosphate. Is that right? Yeah, you're an AP Bio, right? NADP into NADPH. Score. I like when that was 1992. It's amazing I remember that stuff. We don't get into that either. We just say that chemicals have this hidden potential, just like most of you, right? And it can be unlocked and released. Think of gasoline. Gasoline's very visual. You have a gallon of gasoline sitting there. It has the potential to give off a lot of energy, doesn't it? You agree? Before it's burned, it has potential. After it's burned, it exudes a lot of heat, possibly does work by pushing a car, and things are converted. What do you... In the back. Law of conservation of energy, though, is one of the hardest ones for people to understand. When I was holding his hand a second ago, it got a bit awkward after a while. But while I was holding his hand, he was losing energy and I was gaining it. Nothing disappeared, it's transferred. And this law of conservation of energy is actually also related to mass, the law of conservation of mass, except you've just converted energy to mass. And you could take that and say E equals mc squared and talk about Einstein's formulas and stuff, but we're not going to do that. Work, we already saw an example of work. I pushed him around. Temperature, though, is probably the most misunderstood concept in here. People feel like they already understand temperature and they're dead wrong. How many people feel like they already understand temperature? All right, without looking at the board, can you give me your feeling on what energy is? How fast it's moving. Temperature, I like that. Yeah. Temperature is about speed. Look, cursive. Yeah. Temperature is about speed. Are the particles moving quickly? Are the particles moving slowly? You're just nonstop eating. Breaking the law. Temperature is about how fast the particles are moving. Heat is very different. Let's do something for a second. You've got lots of energy today. So take your hand and just go back and forth like this, like you're trying to blow all the, like you're trying to get some smell to go away. Okay. So now towards, for once I want you to do that towards me. Okay. Now, who has a higher temperature? Based off of the speed of the particle, aka the hand. Him. You can't usually see this perspective. His hand is waggling back and forth at a much higher rate. Do you agree? He's getting tired. He had to. He was getting too tired. Now, what would happen if our hands overlapped in space? You keep going faster. Not slow down. No one said slow down. He's getting worn out, by the way. So we're going to come in closer, and they're going to start. They'd start to hit, and eventually they'd sync up. Keep going. You can't like stop. Eventually, they would say, you keep stopping. Okay, I didn't pick the right person. Eventually, just sync up with me for a second. Eventually, they would sync up. Eventually, the two particles would start moving at the same speed, and they wouldn't be smacking each other. There might be a little bit of like, oh, we let go for a second. But for the most part, they sync up when their temperature is equal. So you have a tummy ache. Your mommy brings the thermometer to you. She sticks it under your tongue. It initially feels cold. Slowly, the thermometer gets warmed up by the particles that are hitting it. The particles are at the bottom of your tongue and whatever you call that spot in your mouth. I don't know if it has a name. Probably does. That like well underneath your tongue. What is that? The pit of your mouth. Okay. The pit of despair. No. So the temperatures become equal, and for a minute, energy is flowing from one to the other. When it's flowing, we call it heat. The movement of energy is called heat. As the energy flows out of your tongue and into the thermometer, you are losing heat to the thermometer. The thermometer is gaining heat, and then eventually the thermometer is at the same speed, and you know your temperature. Okay? Let me see if this thing is still hot or not. Yep. So, endo and exothermic, the prefixes give it away a little bit, but if your water is endothermic, is it gaining energy or losing energy? Gaining. So you're heating it up. The water's getting hotter. If your water is exothermic, it is giving or losing energy, so it's getting colder. So let's also write that down in the underneath the notes here. Getting warmer, getting colder. Here we have probably the most common way of calculating energy given off. It's a pretty common demonstration, actually. We might do this next class. Well, how should I? I'm trying to draw something. Anyone guess what I'm drawing? A Dorito. Score. Winner. Yeah. It's not uncommon for me to choose some object to burn. I'm looking at an object I'm thinking about burning right now. It's blue and rectangular. In this case, we often will burn a Dorito. And I don't mean put it over a Bunsen burner. I mean take a match to it, light it, remove the match, and it continues to burn. As it burns, its energy is released. That energy rises up, maybe goes into something above it, and then we can watch this change temperature. Where does the energy in this water come from? The burning Dorito. And then we can figure out how much energy is hiding inside a Dorito and call it calories. And figure out how much energy is hiding inside a piece of food and describe its calorie ability, the amount of energy it can give off. You burn food all of the time. You just do it with the chemicals inside your body. You don't have a little furnace in there, at least not that I know of. Like a little people throwing food into a furnace, oh, that cheeseburger. But that's essentially how we calculate calorie content of food, is we burn it. We burn it inside something called a bomb calorimeter, which we don't, oh yay, the bell. Everything burns at a high enough temperature. So a bomb calorimeter is, you usually fill a container with some sort of really high flammable thing like gasoline, and you burn the gasoline, and you know how much energy the gasoline gives off? Shh, cállate. And then you take the same amount of gasoline, put it back in there, but then you throw the food in. And when you burn the gasoline and the food, it might give off more energy or less, and then you know how much energy is given off by, say, the cheeseburger or the Dunkin' Donuts or the slushie. That's where calorie contents come from. So no, the calorie content of a restaurant, they're going to go on an FDA site. They're going to go on a national site and go, a gram of ground beef has this many calories. We're giving them 127 grams on average. Therefore, it should be this much. A slice of Munster cheese has this much. Therefore, we're giving 4 slices because it's a great hamburger, And a lot of the calorie contents out there, though, they completely leave off any of the sauces you use. Like if you go to, say, a restaurant that makes subs a lot, I'm not going to record the name of the restaurant, all of their advertised calorie contents are without any condiments, any sauce, ketchup, whatever. And all of those sauces are just filled with sugar. Like ketchup, tons of sugar in ketchup. So when you add it, just think about I'm putting sugar packets on my food right now. Red sugar packets. And you kick the calorie content up real fast. System and surroundings, these two terms are about perspective. If you were trying to figure out how much energy the Dorito is giving off, that might be your system. And the surroundings is this water and the air that are taking it in. There are 2 different units. 2 different units? What? Oh, I don't want to know. There are 2 different units for energy. This is the one time we got it right. I typically say the meter is better than the foot, and that Celsius is better than Fahrenheit. Calorie is our unit, and it's better than the joule. The joule is the science unit. The calorie is the American unit. And here's why. If you put 1 calorie into 1 gram of water, the temperature will change 1 degree Celsius. I should make arrows out of those instead. If you put a calorie of energy into a gram of water, the temperature changes 1 degree Celsius. Those numbers are easy to remember, aren't they? They're all 1. If you put 1 gram of water and you want to change it by 1 degree Celsius, you have to put in 4.184 joules, which sounds like a really random amount, doesn't it? That's not a pretty number by any means. Calories and joules are interchangeable just using that ratio, 1 to 4.184. We'll practice that in just a second. While we're on the topic of calories, though, does anyone have like a package with the calorie content on it here? Shocker. Look who does. No, that's okay, great. So I am currently holding up some sort of sugary, bite-sized licorice pieces, strawberry and green apple. They're sour too. Nice. Calorie content: 110 calories per serving. You're only allowed to eat 8 pieces. Man, you can just smell you can almost smell it through the video. It's so intense. Right. That's funny if you think about it. Smell-o-vision is not yet a thing. There are some 4D theaters, though. There are some 4D theaters where you go and they'll actually pump in smell during the movie. Some movie theaters will pump in a light popcorn smell to make you want to eat popcorn while you're there. It's a really creepy way of messing with the audience's perspective and desires. So 110. This is actually kilocalories. This is actually 110 kilocalories, which means 110,000 calories. Every time, and that's not just this, every time you look at one of these packets, yes, it was. Every time we look at one of these packets, you're actually talking about kilocalories in terms of chemistry. In terms of diet, they make it a capital C. The calorie is always a capital. Man, that's an intense smell. The calories are always a capital C. They stopped putting K, C-A-L, because we kept trying to convert it to thousands in our head. And if I ask someone to do 1,700 plus 300, people have to pause. 1,700 plus 300 is 2,000, right? But if I say 170,000 plus 3, I get lost just trying to even convert it. 30,000-ish. I forgot the number. Sorry about that, whoever you are. They get lost in their head and they just give up. And the purpose of putting calorie counts on food is not for you to give up. It's for you to actually be aware of what you're eating, right? The only problem with calorie counts is they don't take into account that my genetic code is different than your genetic code, and the way I break apart starch is different than the way you break apart starch. So, take 2 seconds and convert kilojoules to kilocalories and calories to joules. I'm going to pause while people work. So, my favorite Nick of the entire class period, he took the 5.7, he divided by the kilojoules that are equal to a kilocalorie. It's still a 1 to 4.184 ratio, even though they're both kilos. So you don't have to do all the like kilo to 1,000, switcheroo. And then G Money in the back converted the calories to joules, and he said it'd be 15.6 joules. No, you could also set up as a ratio. A lot of people do that. They say 1 calorie is 4.184 joules. I know there are 5.7 kilocalories. How many kilojoules? I said that backwards. I know 5.7 kilojoules. How many? It's the same ratio. So you can say 1 over 4 is equal to what over what? Yeah, that's perfectly fine. You could do that with moles. You could do that with anything. Anytime you do dimensional analysis, you can actually just write it as 2 ratios. It's a little harder sometimes with those long stoichiometry problems because you have to do a ratio, take an answer, a ratio, take an answer, a ratio. Is there another question? I saw a hand go up and down. So let's take a minute here And imagine that we had a small ice cube and a giant ice cube. And I give you a tiny ice cube about this big. And I give your friend over there, if you want to call her your friend, a big ice cube. They're both ice. Which one's going to take more energy to melt completely into water? The big ice cube. So the fact that the mass makes a difference, that's one of the things we need to pay attention to. What if it was an ice cube versus a chunk of aluminum? Same mass. Which one's going to melt easier, an ice cube or a chunk of aluminum? An ice cube. Even if you put in the same temperature, the ice cube is going to melt a lot easier. How did you know ice cube? You've seen ice melt, you've seen aluminum not melt, right? You've seen aluminum a lot. The temperature also is a factor. So what I have here, I'm trying to cool this piece of aluminum off. It's still pretty warm, which irritates me. I have an aluminum cylinder, which I know you at home can't see. And I'm going to put the aluminum cylinder in the oven and measure its temperature change. We need to write some stuff down about it. I'm a little ahead of myself. Let me just set this down. So there are three components. There's the mass, how much do you want to change the temperature, and what type of substance it is. If you want to change it 1 degree Celsius versus 40, that's a big difference. If you want to change 1 gram versus 500 grams, that's a big difference. And if it's air versus aluminum, those are very different properties. So it breaks down to an equation. Here's the equation. Q equals MCAT is usually what people say, just to remember the order. M stands for mass. C is the capacity. Delta T, have you seen triangle before in your math? No? Okay. That triangle is a Greek letter delta, and it is actually, I don't know, did you know it's the letter D, like the great-great-grandfather of the letter D? You have the triangle, and if you put the triangle on its end, and then you round off the nose, you know, slow evolution. I don't know why I just recorded that, but this is the Greek letter delta, which in math class means change. All right? So how is the temperature changing? We always do the final temperature minus the starting temperature as we use this equation. Here are a bunch of heat capacities. Which substance on the list is the hardest to warm up, requires the most energy? Water. If you want to raise the temperature of water by 1 degree Celsius, you have to, if it's 1 gram, you'd have to put in this much energy. Whereas gold, way less. Gold is only 0.12. Gold easily takes in energy. It's a metal. That's one of the things you learn about metals, right? Is they take in energy really easily, and they transmit it really easily. And if you look at the whole beginning of this list, bam, 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 sand, bam, 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 okay, glass, what? Concrete, huh? Aluminum, great. Magnesium, but most of the beginning things are metals. Metals really conduct energy easily. You don't have to put much in to see a temperature change. Whereas water, you got to put in a lot of energy to make it change by 1 degree Celsius. 40 times more than gold. We're going to do a demonstration of that in a minute with aluminum and water. So what do we need to do? We have a couple temperature probes up here. Which probe is this one? Is it blue or red? Can you see the screen? The red one? You can tell because it's getting hotter, right? So I'm going to take the blue one, the other one, and put it in my piece of aluminum. And while the thermometer's touching the aluminum, what's happening? It's getting into there. We're going to eventually have an approximate temperature for this. It's just still, actually, we're not going to use this one. It's way too hot. Just a second. So we have a chunk of aluminum that's 500 grams. And what is its temperature slowing down? 24 even? Not moving much anymore? So we're going to call it 24. Sounds like the name of a TV show. And then we're going to take this aluminum and we're going to warm it up. How do you warm it up? Put it in the oven. So let's put it in the oven. So what's going on in the oven right now? That chunk of aluminum is gaining Energy. The aluminum foil is also gaining energy. FYI, the aluminum foil weighed 2 grams. It is also 24 degrees Celsius. All right, we're putting energy into both of them. We're going to leave them there for about 5 minutes. That cold chunk of 500 is going to get a lot hotter. So is the aluminum foil. It's going to be very exciting. While we're waiting for it to heat, I want you guys to do this problem on your own. That means read the question, figure out who is heat capacity, who is mass, what's the temperature change, throw them into Q equals MCAT, and solve. I will pause for effect. Do you do the final value minus the initial, or the initial value minus the final? The final minus the initial. Yep. You will occasionally, not in this case, occasionally end up with a delta T that's negative. That's because your substance is getting colder. If your delta T is positive, your substance should be getting hotter. The aluminum in the oven right now should have a delta T that's positive. So let's call on different people. I'm going to call every single one of these people Kate. So I'm going to point at you and just say Kate. So be prepared for that. Hey, Kate, what is the heat capacity? Kate's not responding very quick. What? 0.13? Good job. Yes. All right. Let's go. Kate. Yep. What's the mass? Technically, you're right. Okay, good. And Kate number 3, that's you. Kate number 3, what's our delta T? 11. Yep. 32 minus 21 is 11. Good job. Now we have our MC delta T. Throw it all together in the equation. Tap, tap, tap. Enter. 8.1? That sound about right? Joules. The units often throw people off. We have joules over grams degrees Celsius. I'm going to pretend like this is... Just a second. Yeah, we have grams on top, grams on bottom, degrees Celsius on top, degrees Celsius on bottom. They cancel. Joules don't, so the answer comes out in joules. What was your question? Okay. It does look like a sideways 4. That was important to say. He said sarcastically. All right, next example. Our aluminum chunk is still warming in there. We're going to have several new Kates on this one. Several new Kates. If I haven't called on you yet, Kate, I'm going to call on you in a minute. Yes. It's going to be 4 new peeps. Let me pause while people think. Go through, identify which one's which, reading carefully. You can try to go ahead and plug it in if you want. Well, we let... Wow, I'm getting some sass today. Shocker. Can I get a Q from you, Kate? What's Q? 10.1. Q is energy. You read through there, it says the energy is 10.1 joules. That's the Q. That's how much energy was put into it. And my next Kate looks like you. Yes, eye contact. What is C? You're right, we don't have C. It's the unknown. Nice work. And my next Kate is you. Yep, the mass is 2.8. And my last Kate of the day, back there, do you have the delta T? Madam Kate in the back. 36 minus 21, you are right. It is 15. Yep. So we don't have C, but we've got the other 3 pieces. What you do with it from here is up to you. Maybe you plug the numbers into the equation and divide the pieces over. Maybe someone else algebras it first, moves all the pieces around, so C is by itself. That's fine also. Either way you do it, you should get the same answer. If you didn't get that answer a second ago, this one here, you maybe didn't divide by both things. You just divided by one of them and accidentally multiplied by the other. You might need to throw some parentheses on there. Now that I know my metal's heat capacity, I could do something with this metal. Do you have any idea what metal this would be, looking at its heat capacity? Why would you? I wouldn't, except that I've done this a couple times before. But you could go back to this chart, which I accidentally just skipped. Which metal is 0.24? Silver. Yeah. So you maybe just found some silver. This is a common way of identifying a metal. Like say that Tristan buys his girlfriend a ring and tells her it's gold. All right? She, being the outstanding chemist that she is, takes its mass, warms it up, figures out how much energy put in it, figures out its heat capacity, and it turns out that its heat capacity is darn close to copper. So what it probably is a ring coated in gold, but it's mostly copper, which is very common for gold jewelry. Copper is cheap. Gold is, it's see you later, copper. That was so punny it made me smile. Okay. Hey, I'm recording this. So right now all they hear at home is I bet you're missing this right now. So this is the heat capacity. You can identify unknowns. It's very common also for gold to be mixed with silver. And they get mixed kind of 50-50. We call it white gold. And that would be somewhere between gold and silver. Platinum is also really common. Platinum's not up here. I don't know its heat capacity because I've never met platinum before. It's not in my life. It's a little expensive. All right. Now let's bring the aluminum back. Let me go get the aluminum. That's the blue one. All right. So we have pulled the big chunk of aluminum out. We're now taking its temperature. I took the aluminum foil out with my hand. It's going to take a while for the temperature to climb and become equal. Why didn't I scream like, ah, when I picked the aluminum up with my hand? Less mass. Beautiful. I like that guy. The mass was only 2 grams. This was maybe up in the 90s. All right, I don't know where we're going to end here in a second. That's the maybe up in the... So we could calculate how much heat it can give off when it puts it into my hand. It doesn't end up being much because it's not much mass. If, however, no, I don't usually get to hear other people have hiccups. This always amuses me. Makes me feel better about me. What's the temperature of my aluminum right now? Just reached 50, that's it? That's not very impressive. I was hoping for more. Still climbing pretty rapidly? So we're going to have to wait for it to climb for a while. That's boring. It's definitely not good video. Listening to me talk about a piece of aluminum that's hot. It's going to eventually max out, and we will calculate how much heat it has. We have the mass of the aluminum. We have the heat capacity of the aluminum. And we're going to have the delta T. What's the temperature at right now? So let's go ahead and predict its final at 68. All right? It's going to slowly climb. Maybe it hits 68. Maybe it doesn't. We just don't have time to watch it slowly climb like you guys are doing so intently. But temperature change would be what there? If it goes from 24 to 68, it'd be 44? Yeah. So from 68 to 24 is 44. Someone do some math there. What's 500 times 44 times 0.89? That's like the same as 500 times 40, which would be 500 times 40 is 2,000? 19,500. It's probably good enough. Joules? That is the energy we put into that aluminum. Approximately, because we faked this number. Right? Is it still climbing? Not really? All right. So we're going to do something slightly different now. We're going to actually warm water up in that piece of aluminum. Inside of it. So, So I'm going to warm some water up. I have a tiny beaker of water. That's kind of fun. And so is this the red one or the blue one? coming up in the future. It's always in the future. Isn't your birthday always in the future? The next one. Oh, what? Why do you remember that? So we have the initial temperatures of the two. I put 14 grams of water into there, 500 grams of aluminum. This is the temperature of the aluminum right now. This is the temperature of the water. What is happening between the two? Which way is the energy flowing? Oh, you're observing that as the one temperature goes down, the other temperature goes up, but it's not proportional? It's like 2 to 1, 2 to 1, 2 to 1, 3 to 1? All right. That's a cool observation, actually. And they're getting closer together. Right now, they're 56 and 57. 57. You're right. That's pretty sweet. Getting closer. Ah! They're very close to both being 57-ish. Let's write that down as the final temperature. They're not identical thermometers, and they weren't at the same temperature to start off with. So like they were in air, they were off by about a degree. So we're going to write down, what's the final one for the aluminum there? What's the final for the water? So if you are in this row over, from like Kayla over, I want you to calculate the aluminum's Q. You have the delta T, you have the mass, you have the heat capacity. If you're in Victoria or Ryan's row, either one of the Ryan's row actually, I want you to calculate the Q of the water. It's on the board. One of the Q's is negative, the other Q is positive. Use logic first and then use math second. You are in the water group, you're calculating what the water got. The other half of the class is calculating what the aluminum got or lost. In last period, it's worked perfectly well, almost perfectly. I was about 10% off, which is pretty good. Nadia, do you have an answer over there? Should be a big answer when you get it, too. Should be, Nick, what you got? I mean, Kate, number 5. 1,800? Yeah, but about 1,800? Okay. What about my water people? Waiting. All right. His delta T here, the delta T was about, what, 4.1? Negative 4.1. This delta T is a lot bigger, isn't it? The other delta T has to be a lot more because A, it's a lot less water. So its temperature is going to change a bunch to make up for the difference. Kate, number 7, is working out the math back there. What'd you get? Sorry, this Paul is brought to you by math. $2,600? Okay, you guys aren't. So these answers are not perfectly equal, and I am a little bit irritated by that. It's supposed to be, if one object loses 2,000, the other object gains 2,000. Right now, it looks like the aluminum lost 1,800, and somehow the water gained more than was given. That would be like if I went over to Calvin and said, here's $5, and handed him a $5 bill, and then he looked in his hand, and it turned into 6. Sounds awesome if you like make that magic happen. So that really kind of looks wrong, doesn't it? But I want to point out a sig fig thing, and I know we're not the biggest fans of sig figs on the planet, but this only has 2 sig figs, doesn't it? That means this 8 could be a 9, could be 2,000, and that means this 0, the second sig fig, could be 1,900. They are the same number within the error range. I don't care too terribly much about sig figs. 1800 doesn't look like it's equal to 2000 to me, but they're close. Why are the signs opposite? One gained, one lost. The water gained energy, the aluminum lost it. Worked pretty well. Not great. Last couple pieces, then we're done. Enthalpy is just like heat, except it's per mole. And we're going to go stupid example again. Let's say we've given this young man here a cup and a bucket. And into this cup, he puts 10 grams of gasoline. And into this bucket, he puts 100 grams of gasoline. Which one of these substances is going to give off more energy? The larger one will give off more energy. Let's just make up a number, 2,000 joules. Good luck in your future endeavors.
Thank you. I appreciate it.
This one's going to give off 200 joules. But the ratio there is 20 to 1. It's also 20 to 1. Enthalpy is a ratio of heat to how much you burn or react. Yeah. Yes. It's a ratio of the energy to how much. That ratio should be a constant. And the example I want to give you is if, back to the ice cube, tiny ice cube, right? You were a tiny ice cube girl, person writing on her cell phone nonstop. You were big ice cube. And if I put a little bit amount of heat in your ice cube, I have to put a lot more into your ice cube, but the ratio would be equal to energy over how much. Enthalpy is energy per how much, per mole. And the moles part is missing from your notes, and you need to write that in. It doesn't say per mole there. And it's supposed to. I'm going to write it as an equation. Enthalpy so both ice cubes melt, but the bigger N is, the more moles you have, the more heat you'd have to melt, to put in. So if you have a big ice cube, you have to put a lot of energy in. If you have a tiny ice cube, you put a tiny amount of energy in. But the ratio of energy to size is a constant for the ice cube. So if it takes 10 joules to melt 1 cube, then 4 cubes would take 40 joules. Now, we don't usually write it cubes. We usually convert cubes into grams and grams into moles. So it's a ratio of joules to moles, or kilojoules to moles. That make sense when I said cubes? It's a lot easier to visualize 4 ice cubes than giant chunk. No one gets giant chunks of ice delivered to their house anymore. Used to, like 100 years ago. Yeah, that's why it's called an ice box. You would have a big chunk of ice delivered, and that's how you kept the food cold. The ice would slowly melt, take in the heat. You'd have a cold section of your fridge and a less cold section. Before electricity, just ice was delivered to your house. Look how she's so surprised. I can't convey the amount of like ice box surprise. Yeah. Refrigerator trucks would bring it, like insulated trucks, so that you didn't lose it. We're going to use a calorimeter probably next class, which is just a styrofoam cup, water, and a thermometer. And then you'll measure kind of like we did here, where you'll measure how much energy is transferred. See if you can do it right. Entropy is a term we don't deal with much. Entropy is how much disorder is in a reaction, how things tend to change. We'll talk more about that later, just about disorder. And then these two graphs are given to you in which blah, 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 blah. It's very important. It's going to be an essay question on the test. Make sure you get that one right. Which of these graphs does it look like we're losing energy as the reaction goes on? Yep, the exothermic one. You start here, prepare for loud noise. And as you warm it up, you get more and more and more energy building up, and then BAM! All of that energy is given off, and there's a lot of energy given off. if you were listening, you heard me say prepare for a loud noise. Well, that's not my fault. Over here, there's energy being put in, but the products actually have more energy afterwards. Some of you probably eat food occasionally, and your body converts that food into complex molecules that have more energy than the original pieces. If you break sugar down, you can actually turn sugar into complex proteins and then muscles. It just is not very good. Sugar is not a good source for that. The easiest thing to break apart them into proteins is other proteins. Your body can chop up the proteins into smaller blocks that are just like it and reassemble them into proteins. But these graphs represent endo and exothermic pathways, and we're pretty much at the end of today's notes. Am I done? Yep, because we're not doing chapter 14. Your homework is a piece of paper I'm about to hand to you because the worksheets are all messed up.